First of all, thanks to the organizers, and on behalf of them also, thank you all for being here. We're really excited to have such an amazing set of presenters and posters and sponsors and everyone really coming together to celebrate LatinX people from around the world and their contributions to AI and the unique problems that also come from around the world, which don't always get the focus or attention that they deserve in these types of venues. So just kind of a few announcements and logistics and a few things before we get started. So you're all here, so you probably all registered, but we don't have kind of very high-tech security. So in case you manage to come in without registering, please do just go to the bit.ly site and register. It's also on those little postcards we're handing out. That just really helps us get a good count of who all is here so that we have kind of good information to put forward for next year, and even actually at NeurIPS, where we'll be holding the next LXAI workshop to make sure sponsors can get on board and know that, okay, there's really interest in this community and this is something that is providing value to all of you. So please do register if you haven't already. There are also still kind of a very few limited lunch tickets, so if you haven't registered for the lunch, please do that. That's also at that same link. As you came in, you hopefully got a postcard, a sticker. We do have t-shirts. They're running a little bit late, but at some point just circle back by the registration desk and you'll be able to pick up your t-shirt. And of course, if you tweet or do Facebook or things like that, feel free to follow online and post and tell us what all you think about our program. So a little bit about kind of the submissions and everything that happened. We actually had 78 submissions, almost 2 times what we had for NeurIPS at our last workshop this year, and out of that, it was really hard to make a choice. We had a lot of really fantastic submissions, really from around the world. We ended up with 10 oral presentations and 41 posters, so it's actually a pretty tight acceptance rate. But again, thanks to everyone who submitted and who's here and who's presenting. So quick round of applause to everyone who participated and got in. We'll have 2 oral presentation sessions, that's all in your program, and we have our 41 posters, which will be put up right around the lunch hour. So you'll be able to talk to people kind of after lunch. You'll be able to wander around and see the different posters and talk to everyone there, and then also during the coffee break in the afternoon. So just kind of some quick statistics out of these posters and presentations. Out of the accepted posters, there were actually 10 countries represented. Any guesses which were the most represented countries, just out of curiosity? Peru. Okay, you jumped all the way to the end. So people might guess US. Yes, a lot from US, a lot from Brazil, but Peru did take the cake with 12 accepted posters and presentations. So congratulations to Peru, and again, congratulations to everyone who submitted and had a poster presentation accepted. And of course, none of this would be possible without our travel sponsorship. So we really want to thank all of our sponsors that made this possible. So there were 33 of the people who had posters and oral presentations accepted that are here because of their generosity and helping fund travel and registration and everything, making it possible for everyone to be here. So thank you so much to all of the sponsors who really helped this happen. In terms of the sponsor, sorry, I think I'm behind the slide. So these are our fantastic sponsors, and there's a couple particular sponsor events I wanted to highlight. So of course, our lunch is being funded by CapitalOne, who is also having David Castillo, who's the Managing VP of Machine Learning. He's going to come and give us a keynote during that lunch hour. So please don't miss that. Everything will be here. There'll be buffet tables set up in the back. So it's a continuation and really central part of the day. So please be sure to be here. We're also going to have an industry panel, in particular with some members from Microsoft in the morning that you'll be able to enjoy. And I also wanted to shout out to Facebook for helping coordinate a lot of the travel, and they're also doing our recording for this session. And last but very much not least, we have the great honor of having 3 fantastic keynote speakers highlighting our event. So thanks to Bianca, Eduardo, and Katia for being here. And to not get us, I'm already pushing this 1 minute past schedule, I would like to call up Bianca, who will be our first keynote presenter for the day. Bianca is a research manager at IBM Research Brazil, and she leads the Neural Resource Analytics Group. And the group's mission is to conduct research projects in a data-driven analytics for decision-making in the areas of oil and gas and mining, with a great focus on developing new machine learning workflows to aid geoscientists and discovery of natural resources around the world. So with that, thanks Bianca, and I'll hand it over to you.
Research Brazil, and today I'm going to talk about the work that we do in my group. I'll start with a short introduction to IBM Research Brazil and my group, and then I'll go into the technical content. So actually, IBM Research, it has existed for more than 70 years as an industrial research organization, and it has research labs across the world. I'm sure many of you are familiar with the Almaden Research Lab here in California and the T.J. Watson Research Lab in New York and other places, across the world where IBM Research has been doing great research for a long time. Actually, back in 2010, a group of people from actually the IBM Research in New York decided to open a lab in Brazil. That was the first lab in Latin America and the first in the Southern Hemisphere, and about the same time they opened in Australia as well in 2010. And I was one of the first researchers to join the lab. Actually, I was the first one in Rio de Janeiro. We have labs both in Rio de Janeiro and São Paulo. And we have a great focus on this area that we call natural resources, which is oil and gas, mining, and also agriculture projects. That has to do with the fact that our lab is more into what we call the industrial applied research than basic AI research. So we do work in applications of AI, and there's also people working in nanotechnology applied to these industries that we see we can make a difference in Latin America that are strong industries there. In my group, we actually do, it's called Natural Resources Analytics Research Group, and we have a set of researchers, mostly PhDs, with a background in pattern recognition, machine learning, etc. We have Jorge is here from Peru that's working in the group as well. And our mission is to develop research projects in knowledge-augmented machine learning to aid geoscientists in the discovery of natural resources. So we do what we call this subsurface characterization kind of research. There are many sources of data that you gather, that geoscientists gather, and they do analysis to actually find natural resources, both in mining and for oil and gas. So we do work in this intersection between machine learning and geoscience, and now in the geosciences conferences, there are like tracks in machine learning, and many times we actually do go to those conferences and present our work there as well. So it's kind of strange because in those conferences, we are the machine learning people going to the geoscience conferences. And in machine learning conferences, we have a lot of domain knowledge and expertise about the specific problems in this industry, which are very specific, right? So we work in this intersection. And the way we make this work actually is through partnerships with other companies that are IBM clients and that are interested in developing AI and machine learning for their geoscientists to work on. So IBM does partnerships. We've worked in projects with Shale, with Galp, which is a Portuguese oil company. We've had multiple years projects together with them. And they have the geoscientists, the geologists that work with us in partnerships to help develop these new technologies, right? So it's really an interdisciplinary kind of work where we bring the AI machine learning side and they bring the expertise in the problems that they are going to solve. And we also have projects with the Russian company, and this one is with a mining company in gold, right? So today, I'm going to present some of the work that we do, some of these projects, some of the results, and I hope you bear with me because a lot of that has a lot of details about the specific data that geologists know more about than we do. I'll try to explain more and try to motivate why this is an interesting problem for machine learning, right? Why is it interesting to work in developing research in machine learning specific for this kind of problems? So basically, machine learning has been used for more than 3 decades in general in subsurface characterization. Many times they collect data from what they call well logs, and then they try to infer things from those well logs, which are sensors that you send through the Earth surface through wells, and then you gather information from there, and then you try to figure out, okay, what is the fluid characterization, what is the lithology, which is the type of rocks, and things like that that you find in the subsurface. But now, much more with the like machine learning becoming something that is known by a lot of people, more and more the geoscientists are using those methods from machine learning to interpret seismic images, which is a kind of image that you get from the subsurface, to do sweet spot identification, which is to find where specific resources are, or body modeling, figuring out where specifically the minerals are, bodies of minerals. So, but many times there is a mismatch between the existing state-of-the-art machine learning technologies, which are made for photographs, natural language processing, and the kind of data that we get from the subsurface characterization problems, right? So it opens this opportunity for us to work on different problems in machine learning, develop new methodologies that work for this kind of data, and really be challenged because the domain knowledge expertise needs to be embedded in the process. So the first project that I'll talk about is what we call Goldcorp Cognitive Journey. So Goldcorp made a partnership with IBM to develop many cognitive techniques for their geoscientists, to apply some of the techniques that are already available, like image recognition, et cetera, but also to develop some new methodologies. And the research part was involved my group to help develop some new methodologies for them. And specifically, they were interested in this problem of identifying potential zones of mineralizations. So for that, they gathered different sources of data. So what I'm showing here in the picture is what they call cores of rocks. Basically, they drill some holes and from these holes, they take out these rocks. And the rocks, they examine the rock both visually and also through tests, assays, et cetera, and collect some data, interpret this data. They have shacks full of these rocks, interpreted data, and they put that all in the databases, and then they try to look at all that and interpret, okay, if I found some traces of gold here, I found some fault here, this and that, and then they visualize this in 3D, and they say, okay, I think I have some ore here, right, based on looking at all the data. So the data is very sparse. You have samples of data like that. And then usually the current tools that actually companies have developed for them to work, they don't handle, like they do some modeling, but it's local modeling. They don't handle like the whole, all the data from the mine together to find patterns everywhere there. So what we tasked to do was to say, okay, can we implement and test a modeling workflow based on 3D machine learning techniques for predicting the level of gold mineralization in a specified location within a mine. So you have all the data that you have from the mine. You take as input known geological information, for example, lithology, veining, mineralization, alterations, available from multiple sources, in and around the location of interest. So the way we observe that geologists work, they visualize all this data in 3D, and they start making hypotheses. Okay, since I found this alteration here and this fault here, the process of generating gold, I think it's likely that I'll find gold in this other place, right? So they visualize that, and they try to infer what is the likelihood of finding gold in a specific spot. So what we decided was to say, okay, can we actually use 3D convolutional networks to visualize, like think of it as visualizing the data spatially and making this interpretation of, if I have all this specific pattern, I would find gold in a specific spot. So what I'm showing here is a cloud of this spatial cloud of points. It's a 3D where I show for each point here means I have some kind of data about the specific point that was measured, right? So we have something that took all their data and put in this point cloud representation. And for each point here, I represent all the variables that have been measured according to the points. And this is for a whole mine for which you have done many of those drill holes that you took cores and rocks from that, and you examined the contents of the rock and you recorded that. So from that, we can create training examples that we take all the points for which we know that where they actually have found gold, or points where they have not found gold, right? And then it's a supervised learning mechanism. So we say, okay, this is the prediction that we would like to make is here, and we take all the information around the point to say, okay, this is the input variable, right? What I see around the point where I'm making the prediction is my input variable. So we do that for all the many examples in the mine, both to create positives and negative examples of the presence of gold, right? Where we actually know that there is gold and no gold, and we take all the known information around as predictors. So from that, we create millions of training examples like that for a mine. And we create the cubes to feed the convolutional neural network. So we actually tested two different approaches. One would be what we call the deep learning approach. We take the data, create those cubes, we create a grid-like input, and we feed the neural network. We train it, and then for each point in the mine where we have some data, we can apply this network, and we can say, okay, what is the confidence of finding gold in this point in the mine? This other path here would be if instead of applying the convolutional neural network, I did some feature engineering to say, okay, how many faults do I find within this cube? Like how many, what is the pattern of a specific variable there? Is the variable growing, etc., which are visual patterns that the geologists use to say that they think there might be gold there, right? By the combination of like different alterations happening in a sequence. So we encoded some features that, by talking to them about how they would look for gold patterns, encoded here in this feature engineering, and then we applied different classification models to this vector here of features. And both of them would give us also a classification model with some probability of the gold level. And in the gold level, we have a threshold that we say, what is the chance of finding gold in a certain level in that specific level that they can set, right, to do this training here. So we implemented many different types of 3D CNN architectures to test the approach. We based them on known networks from the literature, but we changed them to deal with this kind of very sparse data. So we tried different, specifically configurations to see what would work better. And bear in mind that this is a big problem because there are millions of training examples in this case, and then each training example, we can make this cube very big, right, with many, depending on how far you want to look for patterns. So it's an expensive problem to train the algorithms. Another issue was how to divide the training data into training task data. So we made the assumption that, in this case, that we wanted to make predictions close to the places where we have data, right? So we partition the data spatially to make sure that the training, the validation, and the test set have similar spatial distributions. Because we want to make sure that, okay, we want to assume that we're making new predictions around the same area where we collected the data. So it would be something like, okay, I have this data now, and if I drill one more point from the same distribution, what would be the chance of finding gold there? And there are many issues that we still want to investigate in this area because, of course, this data set is biased by the fact that those drills, they're not made randomly, right? They are made by, they are already trying to find gold, so each one of them is taken in a certain order. They start with some, and then they start doing one after the other. But unfortunately, we did not have like the timestamp of when they did the drilling, so we could not reconstruct this specific order. So we did, in this case, random sampling, and we assumed that the test would be from the same distribution as the training. For the model validations, this is a very hard problem to predict gold. Like even for geologists, it's very hard to, given this data, to know where a certain spot would have gold. So if we only look at some metrics like accuracy, AUC, we are not going to deal with the true positive, false positive issues that, of course, are important here. So we actually did some metrics that were more cost sensitive in the sense that we put into what would be the gain if you actually found a drill hole with gold, and what would be the cost to drill a hole, right? Because if not, you would say just drill holes everywhere and you're going to find gold. No, because each drill costs like $45,000. So every year they have a budget to select some of drills to do. And those, and then if they find, then they have a benefit for the company, right? So we want to maximize this benefit. We want to not have a lot of drills, but those drills that we do actually are good. So the business value is actually, the gain times the true positive minus the cost times all the positives. All the ones that you predict are positives are going to incur a cost, right? And then we normalize that by the best possible model, which would be the one that gets all the drill holes correct. Doesn't get anyone wrong. Then we did a comparison. There are many more experiments than this. This is one of them where we tried to look into what would be the effect of using different variables and with different models. And we did the ranking by the business value, right? So this is showing that the 3D convolutional network was getting slightly better results than the logistic regression with only gold, right? It has a better business value because it has a lower false positive rate here. So we looked into, like I said, we tried models that were traditional machine learning with the encoded features, which was the case here for the logistic regression. And we tried models that were more sophisticated. So, and in many of in this case, we didn't do a statistical validation. We did, because we did only one sampling, and it took like a very long time to run some of those experiments specifically with the 3D convolutional neural network. We also compare with the logistic regression using all the variables actually was doing worse than the logistic regression using only gold. So it was not, the variables that we added were not actually helping the model as much as that. Gold is actually one of the predictors, right? Because if I know I have gold in one place, then of course it's correlated with the gold in another place. So gold is one of the inputs to the model itself. I don't know if I made it clear afterwards. It's like a time series, right? You predict the next one based on the previous value that you have. And for the geologists, the gold itself, of course, is very telling. If you have gold here and gold here, then you might find gold in between, right? Something like that. And the challenge is to be able to add these other variables and see an improvement in the model, which we were able to do to some extent. And here is the baseline model. This is actually what they were using before. And this was actually really bad because they, basically because it doesn't weight very well the positives versus the negatives for the costs, right? They were just doing an average of the gold values, but they were not taking into account that you actually have to predict, be more positive than negative in this case to get better results. So in terms of the baseline, we did do much better. And this was done by hand by the geologists. They basically draw some shapes and they average the results with some interpolation across the shape. Right? So this was a very positive result that we were able to improve that by a lot. And here's some qualitative analysis that they did based on the results that they used to have like this, and now when we were able to automate the process and have predictions in places where they were not even looking at because they didn't automate the process of generating the models in the same fashion that we did, right? So they start looking into, okay, now the model is very confident in predicting wastes, which they were not before, and now they can basically rule out a lot of the data that they did not rule out afterwards, and things like that, right? So now they have access to this tool, and it's not something that they completely, let's say, forget all the analysis that they normally do, but they use that as one more source of information that the model is giving them based on this to say, okay, here's some place that you might look for that you would not normally look for, but this is where the model is making a good prediction for you. And actually, this project was awarded some awards by mining experts, Mining Magazine. This was in collaboration. We work in Brazil with collaboration with IBM Canada from the research part. I mean, the research part was in Brazil, and the IBM Canada was doing the delivery of the project there to the client. So we did get some awards this year and last year based on this work. And Goldcorp was reporting already, doing some drilling based on the project and getting good results of finding more gold than they used to find from previous years, right, in the new drillings. So now I'm going to move from gold to oil shale exploration. So this is a similar, let's say, kind of problem in terms of machine learning, but in terms of data and domain, they changed a little bit. And also machine learning, we took some different approaches here. Basically, the idea is, again, you have like many wells that have already been drilled in the past in one field, and you have the results from them, and you want to say, okay, let me apply machine learning to see if I can choose better the completion parameters, which are like the length of the well, the number of stages of the well, many decisions that they have to make, and also the locations, right? Pick the locations where that would maximize the production. And again, this is for an area that has already been drilled. So there are many fields. It's not for some new field, right? There are many fields where there are many wells that have been drilled in the past, vertical wells that are conventional, and now the companies are going back to them and saying, can we actually extract more from the same area? So this is actually a good thing in terms of environmental, because you go to the same area that has already been developed to extract more and with better results. And basically, there are different sources of data that are available for the shale fields, right? Similar to the gold case, they have many petrophysical measurements and geological interpretations that they call well logs. So this would be going from the surface, going down. They measure things like resistivity, gamma ray, other variables, physical variables that they later interpret, and they say, okay, this is a layer of a specific type of rock, this is a layer of a specific type of rock, and this is another layer, right? This would be looking vertically. Here is a field looking from above. You see where all the wells are. Both the blue ones are the vertical wells for which we have physical measurements, and the red ones are horizontal wells for which you have the physical measurements. And the green ones are the wells for which we have the known production. So they are wells that have been producing oil, and we know how much they actually have been producing over time. So the idea is saying, okay, can we take all this data and try build models to help understand what is going on? And if I want to build a new well, I optimize where I put the well, what would be the size of the well, etc. So this is a workflow that we have developed, and we have published and actually patented some of this as well. So we have the data sources. We integrate the horizontal well logs and vertical well logs into one feature map generator that we can use for doing machine learning. So we do a feature extraction here. So it's different from the Goldcorp case where we are actually applying deep learning, and we don't do feature extraction in some of the cases. Here we do a feature extraction phase. And we have the completions and engineering data and the well production data. We integrate this in one data set where we use the petrophysical features and the completions data to predict what would be the production data. And for this, we use both black box models. Sorry, I forgot to. So from here, we select the data. Here, we extract the key characteristics and features from the logs. Here, we interpolate the features onto the producing wells, because the producing wells are different from the wells where we have the features. Here, we create the models, and here in this approach, we use both black box machine learning models, as well as machine learning models with domain constraints, where we put some expert knowledge into the models. And then we have an analysis engine where we can analyze the effects of different parameters on the production, and also look at the best locations for drilling the well. So we did the work together with Shale to validate this in an area that is known as the Permian Basin in Texas. And we use different petrophysical well logs that come from those wells, and both horizontal and vertical. So in this case here, you can see that in terms of the data, it's different from the Goldcorp case. There we had thousands of drills where we could create millions of training examples, whereas here we only have a few wells, and some wells don't have measurements, things like that. So in the end, we don't have that many data. So although they are similar in some sense, when you actually do apply the methods, you see that there is many different in the kind of methods that we apply. It would be difficult to apply some deep learning method in this kind of data set than in the other one that was much larger. And we have 152 producing horizontal wells, which actually, this is the labels that we have for our model, right? We wanted to train on predicting production. So it's very few labels of examples, where in the other case, we have thousands or millions of gold samples of assays that we know whether or not is gold, right? And we can train the models like that. So here, we do leave one out, cross-validation. So again, we take like each well that we know about, we leave it out, and we train as if we had all the wells in the field except for that one. We don't take into account the temporal aspect of the drilling. We do it as if you had everything and you said, okay, what if I drill one more well? How well would I be able to predict that? And these results actually have been published already in some, the SPE Annual Technical Conference and the SPE Journal, which is Society for Petroleum Engineering. So as I said many times, we do publish in petroleum and geology conferences. The petrophysical feature generator, basically I said before, we have wells for which we have the cumulative production, and we have wells for which we have petrophysical measurements, in this case, the gamma ray data set. So we have to actually, in order to create a machine learning model, we need to have both of them in the same location, right? So for each of the producing wells, we need to know what would be the input variable that we would use for that. So we interpolate locally around that well in a grid all the measurements that we have, and we have one value that we use. So we don't do like in the Goldcorp case where we take all of that as an input cube. We do have one value that we use as input to the model. This has to do with the fact that we have much less data to train the model. So if we leave it very complicated, we won't be able to train. So then I'm moving now to this predictive modeling engine part, where basically we tried black box machine learning models from libraries, Caret, etc. We tried many ones with the data that we have created. But we also introduced this idea of using generalized additive models and shape-constrained additive models, which come from the statistics literature. So basically, they fit a spline for each one of the variables. And the nice thing is that you can do you can create an interaction. In this case, we put the X and Y location as input as well to the model with an interaction. So we have a spline here that would model what would be the effect of the location on the production. And similarly, we have for the length of the well for the proppant injected, which is something that they inject in the well to make it produce, the location, and the number of days the well that has been shut, and the GR, which is the petrophysical measurements that we want to also see whether they have an effect on the production. And we tried both these generalized additive models where we fit splines, each one of them. Also the shape-constrained additive models where instead of, we actually say that there is a specific form for the function. So the function is monotonic in some of the variables. So we say, for example, that the proppant injection actually has to increase the production of the well, because it's impossible in practice that if you inject more proppant, you're not going to increase the production. And since we have a small data set, if we leave that open, the model might find something that it's not physically possible. So we put these constraints in order to make it easier to learn with less data than we actually have. So that's the nice thing about this kind of model, the shape-constrained additive model. So here we're showing some of the results. So this is the generalized additive model, and we use the RMSE as the metric for error. So this would be the error on the production estimation of a well with using this specific model and using the different types of gamma rays interpolations that we have. So I didn't go into a lot of detail, but here we use only all the wells. Here we use the vertical gamma rays, and here we use no gamma rays. So you look into what would be the error of the model like that. And basically, here is the random forest, which is from the black box, was the one that gave the best results. And here is an SVM with a linear kernel. So the scam actually gave the best results using the GR as one of the features in the model, which was nice because we were trying to show that using the gamma ray from the horizontal wells would actually improve the accuracy of the model, which is something that had not been done in the literature before. And the fact that the shape constraint gave better results was also very interesting because if you look at these are effect plots of what would be the effect of injecting more proppant in the well, how that affects the production, right? So, for example, here it's showing that as you increase the amount of proppant, you actually increase the production. These are confidence bands. And the length of the well, similarly, when you increase the length of the well, you would expect from the geologists, they would expect that as you increase the length of the well, you also increase the production. But then if you look at this is going down, right? So there's something strange here. But we actually have very few data points here in this region. So when we use the shape constraint method, we are able to say, no, there has to be a monotonically increased relationship. So it learns this specific function here, where it goes down and then it stabilizes with like a larger confidence band, because it doesn't know very much about this area, because it hasn't seen a lot of wells with like 8,000 or 10,000 as the length of the well, right? But at least it's showing something that makes sense. As you increase the length, the production should not go down. And here probably it was because of noise, some other variable that was not considered in the model that was making this go down by some other reason, right? That was not taken into account. And as we include the constraints, we make these curves look much better to the geoscientists, right? It makes sense to them that this would, this one has to go down, etc. And at the same time, we improve the accuracy of the model on new data, on unseen data. So it's a kind of regularization that we are doing by doing these shape constraints, and it improves the results. Here we're showing the maps of predicted production. As we change some of the parameters, we change the production. But this allows to look into the potential locations that would give more production than other locations, given the completion parameters. So in the tool that is now IBM is commercializing for Sweet Spot, you can actually play with the different scenarios and visualize different things, etc., based on this analysis. So in the Sweet Spot, we presented this methodology for well log data integration, predictive modeling, evaluation of what-if scenarios, and sweet spot identification. We applied this to a real data set, and we were able to successfully integrate the data and to train the black box and interpretable models, which are the GAMs, the generalized additive models, and the scams. And the scams actually did better than the random forest and SVMs on this data set, for the reasons that you can encode some of the physical constraints and knowledge about the domain into the problem. And we believe that this methodology can be extended to other problems. So now, to finish, I'll show some other work that my team has been doing using generalized, sorry, not generalized. I was talking about generalized before. So before I was talking about generalized additive model GAMs, GAMs. Now this is work using GANs, which are more famous, I guess, in the ICML community. So it's generative adversarial networks. So here we are working with another source of data that for the oil and gas industry is important, which is the seismic images. And I don't know if people are familiar. Basically, there are methods of getting underground images that would look similarly to, let's say, an ultrasound, but they are doing by generating seismic waves, and then you actually have hydrophones that recover those waves here. And then there's a process that is done to reconstruct, and what you get out is something like this, right? So the geoscientists, they interpreted these images, and they see like what are the rock layers underneath the earth based on that. These are actually 3D in many cases. Here I'm showing a 2D example. So a lot of the work that my group does now is working with seismic images, both in trying to learn the interpretations, which I'm not showing today. Say, given an image like that, give back what would be the rock layers, right? We have done a lot of work like that. Some people from the team started working on saying, can we generate synthetic seismic images, which is something that had not been done before to the best of our knowledge in terms of taking the work that has been done with GANs for photographs and other kinds of data and say, can we apply that to generate seismic image? So they did initial work and published in this European conference on geology, exploration geology. They just presented that last week there. Basically, the idea is the basic GAN idea of saying the geologists, they communicate to each other through sketches of what would be the strata of the rocks. And they say, okay, if I look at a salt dome, it's going to look like this, right? And they draw something like that. And they would like to be able to say, okay, given this sketch, try to look for this sketch in the seismic and see if you find any patterns like that. So that would be one application of this idea of the synthetic image, right? Basically, they would be able to draw something and generate a seismic image, and that seismic image could be used both for enhancing training of the methods that we use for modeling, but also for searching to scan seismic cubes, looking for similar structures that they would like to sketch. So we trained this to say, okay, given the sketch and there is a generator network that generates a possible image, right? And then this network is trying to detect whether or not this is fake. So the generator network is going to try to improve this process until it generates very good images. So we have to have these pairs of real seismic and what would be the sketch that the geoscientists would do. So we did collect a data set of about 750 pairs like that to train this model. And here is some of the results, right? So this is the original image, and these are different types of sketches that people could have done that would be representative of this image. So the network sees this and also sees these different types of sketches. We tried training with different types also to see which ones kind of would work better. And here is the output for that the network would see. For this sketch, it generates this image. Sorry, this is the, here would be one sketch, and this is the image that it generates, this is a sketch, this would be the image, etc. So for us, it's difficult to actually to see if this makes sense, right? Because we're not geologists. But for the people that have seen this, for them it looks quite realistic. And if you look, here is the seismic, the real seismic, and this is the other, the synthetic seismic. So here, let's see if it's gonna. Yeah, so here's the example, the tool that you can draw and generates this image. So the idea later is that you're going to be able to take this and then look for this pattern in the many seismic images data set that are available. Actually, there are many seismic images, and they are 3D, so they are huge, right? So looking for patterns is not very easy. So this is a way that they would be able to do. But like I said, we're just starting this research, so it has not been validated like the other methods that we already work with the clients to work. So this is, we just had this first conference paper. Okay, so I hope that I was able to, show that there are many challenges in subsurface characterization that can be addressed by the use of machine learning techniques, but it's not very easy many times to use off-the-shelf something that already exists and apply to the problems, because you really have to understand the domain, the kinds of data, and you move into another world, which is the subsurface world, where you have these problems of sparsity, small samples of data, low resolution images. You have spatial correlation, so the points that are measured are nearby, and they are, there is a problem of bias that, the points that are measured is because people actually wanted to measure them for some reason. It's not a random sample. There is context dependence, so when you train a model for one region, let's say if you take a specific oil field in one place and you train a model for that, if you try to use that same model for another oil field, it's not going to work because it's a different geology, and then the types of rocks are different, so there are many difficulties in transferring models from one region to another. So in my group, we are currently working more on trying to rigorously assess this kind of spatial bias, make it easier to transfer models from one region to another by characterizing, what we call analog regions, right? Regions where the same models would apply. And our focus is to say, if we take all the available data that is out there from public sites, from seismic images, from well logs, et cetera, from subsurface data, if we train models using all of them instead of using specific areas like we have been doing up to now, can we do better than, let's say, train a model for one region specifically? Like I said, it's difficult because it's not the same geology, right? So we need to have a principal way of saying, we can use data from these regions because they are similar, et cetera. So that's the goal that we are trying to go further, and we think there is a lot of space still for doing research to advance this area. And also people that really understand machine learning and not be only the geoscientists that are taking the machine learning models and applying without really knowing the math or the behind and things like that. So we work in partnership with them. I think that this is what works better. Okay, so that's it. Thank you. Gracias. Any questions?
Hi, Bianca. Thank you for your presentation. I had one question about the shale exploration project, and this is regarding physical constraints and how they're applied to your models. Because I think in the table for your GANs model, it's mentioned that physical constraints are applied as interactive terms. So I just wanted to ask if you can maybe give some examples of what these physical constraints are and how they're applied, because I would imagine one constraint would be limiting the length of horizontal drilling as to not hit a water aquifer, for example, but that's just my guess. And are the same physical constraints applied to every well in the Permian Basin, or are they specific to certain wells or cluster of wells? Thank you.
Thanks. Thanks for the question. Very good points. So right now the physical constraints that we looked at were only those to say that there is a monotonic relationship between two variables. That said, for example, that if one variable increases, then this other variable has to increase. So it's not like a hard constraint on, let's say, what would be the length of the well, but actually this actually is a good idea. It does make a lot of sense also to add some other constraints to the model that were not. In this case, the model was trying to predict production, and we didn't take into consideration, let's say, whether or not the well would cross an area, for example. But I think that that would make sense. In this case, we are assuming that all the wells are in this one geological layer, which has already been identified, which is the shale layer, right? So we are not even assuming that the well would go out of that, right? It would be like one horizontal well within that layer. To make it more general, then, yeah, we would have to say, okay, you could go into different layers, but you cannot go through that one, things like that, right? That would be more like an optimization kind of problem, I think. So right now, the only one constraint that we look into is the monotonic increasing constraint. That's it. Yeah. No question?